photon of light with a frequency of 8.84 times 10 to the 14 hertz, or seconds to the minus 1. So in question 1, we converted frequency into wavelength. In question 2, we're asked to convert frequency into energy. Remember that for any photon, if you know the wavelength, or you know the frequency, or you know the energy, you can calculate the other two. So in this case, we want to find the energy. Well, this we can do using E equals h nu. All right, if you were going to convert between wavelength and energy, you'd use E equals hc over lambda. So in this case, E equals h nu. E is the energy of a single photon in joules. H is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. And nu is the frequency in hertz. So in this case, we can just plug in. E is what we're looking for. H again is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. And the frequency, nu, is given in hertz. Again, just like in the previous question, if it was given in megahertz, we'd have to change it to hertz. But in this case, it's just given in hertz, so we can just plug it in. 8.84 times 10 to the 14 seconds to the minus 1, which is a hertz. All right, when we do that, we find that E equals 5.86 times 10 to the minus 19 joules. So there are very few, or there's a very small amount of energy in each photon, which means that in order to have an appreciable amount of energy, you need lots of photons, right? 10 to the minus 19 joules is not a lot of energy for a single photon.